So now you can see my screen, right?
Yes.
Okay. Okay, so let's just get started. Okay, so this class we're gonna continue this wastewater treatment process. So if we do a quick recap, last class we started introducing some contents about the wastewater. So we first talk about the different properties of the wastewater. For example, the physical properties. We talked about the color, the odor, the amount of solids, and then suspended solids, and so on, right? And then in terms of the chemical properties, we talked about the BOD, and nitrogen, phosphorus. So then we introduced the regulations or the standards regarding the wastewater, right? So the EPA requires that the wastewater coming out of the wastewater treatment plant or the effluent coming out of the wastewater treatment plant have to satisfy this 45 or 30 milligram per liter standard. So 45 being the weekly average, and then 30 being the monthly average. So the weekly average is higher than the monthly average, mainly because we need to consider the fluctuations of the pollutants inside the wastewater, right? So this value or these values apply both for the suspended solids and the BOD. So then we showed a short video about the municipal wastewater treatment system, right? So it's a wastewater treatment plant. It has different components inside. That includes a screening, comminutor, grid chamber, primary clarifier, and then aeration tank, secondary clarifier, disinfection, and so on. So then we said that for the wastewater treatment plant, we actually categorize them into primary treatment, secondary treatment, or tertiary treatment, and so on, right? So primary treatment actually just involve these process that's written in red. So they include screening, comminutor, grid chamber, and primary clarifier. And then secondary treatment includes the aeration tank and then the secondary clarifier. Disinfection is normally categorized as the tertiary treatment. So depending on the requirement for the final effluent, so we will use different levels of the treatment processes, but the EPA regulates that the wastewater treatment plant has to have a secondary treatment. So basically, it means that the wastewater treatment plant in the United States will include both the primary treatment and the secondary treatment, right? So sometimes for these screening, comminutor, or grid chamber processes, people also call them as the pre-treatment, but some people also call or categorize them as a part of the primary treatment. So then we discussed this on-site treatment method. So basically, the most widely used treatment device is the septic tank, right? So it occupies or it represents 80 to 90% of all the treatment or on-site treatment facilities. And right now in the United States, they still play a very important role, right? So they serve around a quarter of the population. And they're also very helpful because if the residential area, let's say the households are far away from the wastewater treatment plant, then it's going to cost a lot to build the sewage or the sewer all the way to the treatment plant. So septic tank is also very effective in terms of treating localized polluted water. The only thing is that we need to properly maintain them, right? So to clean them and also to replace them before their lifetime. Otherwise, the overflown wastewater is going to pollute the groundwater. Okay, so in this class, we're just going to focus on the municipal wastewater treatment facility. We're going to talk a little bit more about these different steps and also show some basic calculations related to the design of these systems, especially on the primary clarifier, aeration tank, and secondary clarifier. Okay, so basically, this is a schematic diagram of the, I would say, the modern day wastewater treatment plant, right? So it includes the primary treatment and secondary treatment, right? So you see outside the secondary treatment, like disinfection, they are categorized as the tertiary treatment. So, and then inside the primary treatment, then there are screens, bar screens, or the spar racks to remove the larger particles, combinator to further cut these remaining larger particles to uniform sized solids, then grit chamber to further remove the particles, primary clarifier to settle down the remaining particles. And then since we still have a lot of BOD, right, organics in the wastewater, so we'll introduce them to the secondary treatment, which is the aeration tank. So inside the aeration tank here, as that video yesterday showed, so it's basically bacteria enjoying their unlimited food, right? So basically here we pump in air, so to provide enough oxygen, and at the same time, there will be bacteria eating off the remaining BOD, because one major goal for the wastewater treatment facility is to reduce the BOD, the amount of BOD in the wastewater, right? So they can consume the BOD here, and at the same time, the bacteria, through their respiration, they populate themselves too, right? So they're also going to have this population growth of the bacteria until the bacteria themselves become suspended solids that we have to remove them, right? So that's why after the BOD are being treated in the aeration tank, we send them into the secondary clarifier because now the bacteria are large enough that they can settle down just by gravity, right? And then the effluent from the secondary clarifier are treated as, let's say, are regarded as the treated water. So now they should have a relatively lower BOD, and you can directly discharge them to surface water, let's say to lakes or to rivers. And sometimes people also disinfect them. But then this is not the end yet, because if you consider inside the aeration tank, we need bacteria, actually a large amount of bacteria to consume the organics. So where do those bacteria come from, right? So basically they're coming from the bottom of the secondary clarifier, because now at this stage, most of the suspended solids here are going to be the bacteria that propagated inside the aeration tank. So now what people do is that they concentrate this sludge here. So but by saying this sludge, or people also call them as activated sludge, because there is active let's say, microorganism in there, right? So they're activated. They're sludge, basically, they are concentrated solution, so they're not solid yet, right? So that's why you can still introduce or pump this part of the sludge, and then let's say a fraction of them, you can introduce them back to the inlet of the aeration tank. So in this way, you provide the bacteria directly at the entrance of the aeration tank. So the bacteria can directly react with the organics. And then the remaining sludge can be pumped to the sludge treatment and further for disposal, right? The same thing for the residue, I would say the sludge at the bottom of the primary clarifier, because here, I would say most of these solids are just going to be the, let's say, the suspended solids in the wastewater, not necessarily bacteria, right? So then you can concentrate these two streams and then further treat them or directly dispose them, right? So we'll just go through these components one by one. There are some more detailed introductions. So the first one is the bar screens or core screens or bar racks. So these systems act as the first barrier to, let's say, block the larger chunks of the waste in the wastewater, right? So these bar racks normally have openings of 5 to 40 millimeter, and then people use at least two channels. So the reason why we have two channels is to add somewhat like a safe, right? Because if one channel got blocked by so much of these solids, then we have to maintain them, pull them out, right? Stop the water going through the channel. So at least you have another channel to still let the wastewater to go through, right? So this is how it works. It just blocks larger pieces of objects, right? So here are some pictures of these bar racks. So normally these bar racks act as somewhat like a track. So I would say the whole racks are going to always move. So it's always lifting up, and then at the same time, it's just like the tracks of the let's say the heavy machines, right? So it's always rotating, right? So on the other side, it removes these larger chunks of the solids, and then so that you have clean bar racks at the bottom of this flow channel here, so that you can continuously rotate them so that you can remove these larger pieces of waste. So we mentioned that sometimes you have to maintain the channel, right? So are there really scenarios that we have to pull one channel out and then maintain them? Right. So this is an interesting news. So a few years ago, there's a wastewater treatment plant in South Carolina. It's called Low Country's Wastewater Treatment Plant. So they discovered a massive collection of baby wipes at the bar screen, right? So basically, maybe during that specific time, then people decided to dump in a lot of baby wipes. So, and then the baby wipes are larger pieces of solids, right? So you cannot really remove them by the bar racks. It's just the whole piece is going to get stuck there, right? So indeed, regarding the baby wipes, there are flushable and non-flushable baby wipes, right? So at some time point in the future, if you have kids, right? So pay attention whether you can flush them or not. So otherwise, it's going to be a huge burden to the wastewater treatment plant. So then the next step is the comminutor. So what the comminutor does is that it's going to grind the remaining larger pieces of particles into smaller ones so that they have a uniform size. So until their size is, let's say, 1/4 to 3/8 inch, right? So in terms of millimeter, that's around, I would say, 6 millimeter to 10 millimeter, right? So 1 centimeter. So the major goal is that once their sizes are uniform, then when you're trying to settle them or when you're trying to use some gravitational or inertial methods to remove them, then these particles are going to behave relatively similar in a similar way. So you can use the same or similar residence time or similar mechanism to remove all of these particles, right? So this is how the comminutor looks like. So they're made of these blades here, so they can cut these remaining particles, right? Remaining chunks of solids into uniform sizes, okay? So this is just one extra step so that you can generate a uniform distribution of these solids. So then the next step is a grid chamber. So although we call it as a chamber, it's more like a flow channel. So this is just a cross-section view of the grid chamber, right? So in actual situation, it's just like a flow channel. So the water go from one side and exits through the other side. So here is a schematic diagram of this grid chamber. So water will go through this side. This is the influent, and then here on this side, this is the effluent, right? So water will just peacefully go through here. But then at the same time, we actually add this air diffuser assembly on the side of this grid chamber. So as you can imagine, the air is going to bubble through, right? So it's going to drag the water to go up on this side. And because of this drag force, so it's going to force the water to have this spiraling movement, right? So because on this side of the wall here, the water is always trying to go up. So because of this mass balance, right, the water go up on this side, the water has to go down on the other side. So it's going to create this spiraling movement of the water. So once you have spiraling or this rotation, then you can spin out these larger particles, right? So it's just like a washing machine where you get these larger particles to get collected. And then at the bottom, there's this hopper here to collect these solids, right? So this is how the grid chamber looks like. And This is again the cross-sectional view of the grid chamber, right? So you have this air diffuser generating bubbles up, and then it's going to rotate the water. So the reason why we're pumping air is on the one hand to create this spiraling movement, but on the other hand, we also want to introduce some dissolved oxygen into this wastewater here, because later on we need to use bacteria to consume the organics inside, right? So after the grid chamber, then we get to this primary treatment or the primary clarifier. So if you just look at this schematic diagram again, right? So we talk about the springs, commutator, grid chamber, and the next step is the primary clarifier. So the primary clarifier basically remove particles just based on sedimentation, based on the gravity. So if you take a look at this picture here. So I think in the beginning, when we talk about the mass balance, we give an example problem. So we had a primary clarifier that removes suspended solids with certain flow rate. The influent suspended solids 200 milligram per liter. Effluent is 80 milligram per liter. We were trying to calculate the efficiency for this primary clarifier. We find out that it's 60%, right? So it's just 200 minus 80 divided by 200, right? So the primary clarifier removes the particles just based on gravity. So what happens inside, let's say if we have a circular primary clarifier, then the influent water, right? So the water coming out of the grid chamber will be introduced from the center. And then at the same time, the water is going to, because of that, the water is going to flow to the edge, right? So we call these as a weir wall. So the water is going to flow towards the weir wall. And then the suspended solid inside the water is going to settle down based on gravity, right? So basically at the bottom of this primary clarifier, these are just settled suspended solids. Okay, so since we talk about the sedimentation, right? So when we discuss the sedimentation basin, we said that there's a major or very important parameter related to the design of the sedimentation basin, which is the overflow rate, right? So if you recall, for the sedimentation basin of the drinking water treatment facility, we said that we could treat the sedimentation basin as a rectangular shaped water reservoir, right? So there's going to be water or suspended solids settling down, and then there's a critical settling velocity, where if the particle's settling velocity is higher than that critical settling velocity, they're going to settle down. And if the particle's settling velocity is lower or slower than that critical velocity, then they're going to penetrate through the sedimentation basin, right? So we derive that critical velocity, that is just the height of the sedimentation basin divided by the time, the residence time of the water, right? And further, the residence time is volume divided by the flow rate. If you plug that in, and then you can find out that the overflow rate, or this critical settler velocity, is just the flow rate divided by the surface area, right? So this is how we defined this overflow rate for the sedimentation basin. And it is exactly the same, or even the same equation for the primary clarifier, right? So because we're using the same mechanism to remove the particles. So for the primary clarifier design, people also specify this overflow rate, and then you can use the flow rate to determine what surface area we need for this primary clarifier, right? So here are some design parameters. For example, you can have rectangular shaped primary clarifiers or circular shaped primary clarifiers. So these are some recommended design parameters. And then there is this average overflow rates, right? So we specify them so that we can remove the suspended solids in the primary clarifier. So people normally use a value of 25 to 60 meter per day. So what this basically means is that these particles with this critical velocity, right, is going to settle on average 25 to 60 meters over a 1 day time. But on the other hand, the retention time, right, the residence time of the particle in the primary clarifier is just 1.5 to 2.5 hours. So it's somewhat like like 10% of a day, right? So they will on average settle down by 2.5 to 6 meter during this entire retention time. So as we said, the primary clarifier remove particles based on gravity. So if you consider gravity, it's actually not that very efficient to remove particles, especially small particles. So then, because of that, for the primary clarifiers, they have on average suspended solid removal efficiency of 50 to 60%. And then they can also remove some of the BOD, the organics, mainly because some of the organics exist as suspended solids, right? But the primary clarifier on average can only remove around 30 to 35% because a lot of these organics exist as a part of the solution, right? So they're not existing as solids. They just dissolve inside the water. Similar to sugar, right? Sucrose, they do not exist in the form of suspended solids, but they are counted as BOD. Okay, so here, this is a short, let's say, practice problem or example of how we design the primary clarifier. So maybe let's spend 2 minutes to just look at this problem and then think about how we can solve it. Okay, so let's take a look at this problem. So I would say for this one, it is relatively straightforward, right? So it's just lay out all the conditions and then we can try to come up with a design. So it's asking us to determine the surface area of a primary clarifier tank or primary setting tank size to handle a maximum hourly flow rate of this value at an overflow rate of 60 meter per day, right? So first, let's look at the first part of this problem. It's just asking us for this surface area. So if we just lay out this equation here, so we know that this overflow rate, this V, should equal Q divided by A, right? So we have this Q here, and then this V, the overflow rate is over here, right? So you have these two, and then you can directly get the surface area. So the only thing we need to pay attention is the units, right? So A equals Q divided by V. And then this Q here, this is based on per seconds, and then overflow rate is based on per day. So we need to convert this value, right? 0.57. We need to consider that for each day, there are 24 hours, and each hour there's 3,600 seconds, right? So you need to multiply this by 24, and then 3,600. And then you divide that by the overflow rate. That's 60. right? So then you can find out that the final answer is it's 821 meters squared. Okay, so this is quite straightforward. And then it's saying that further the effective tank depth is 3 meters. So now we're talking about first, this is surface area, right? So now it has a depth. For example, you have the rectangular shaped, right, or cylindrical shaped. So now it's giving you the depth. So it's asking what is the effective theoretical retention time. So retention time is just resonance time. So the resonance time equals the volume. Let's say, just write it as volume. And then that divided by the flow rate, right? So further, the volume of the tank equals the area, surface area multiplied by the height or depth of this tank, right? Divided by the flow rate. So you can plug in these values here. You have the area, you have the height, and then you can divide that by the flow rate. So, and then basically that's based on seconds. And then you can find out that it's a pretty large number. So if we convert it to hours, then that's 1.2 hours. Okay, so this is related to the design of the primary clarifier. So we need to pay attention that the overflow rate is the parameter that's connecting all of these calculations, right? Any questions here? Okay. All right, so here, I mean, if we're in the classroom, we would have a quiz. But here I managed to somehow create a pool. Let me see. Let me launch this pool here. So you can just make your selection and then submit your answer. So can you see the quiz question, the poll question here? Okay, I see that all provided the answer. Okay, so the correct answer should be overflow rate. So mention that the overflow rate basically links the flow rate and the surface area, right? So that's the most important parameter when we're talking about systems using gravitation or the sedimentation, right? So for the sedimentation basin design, we use the overflow rate. And the same thing for the primary clarifier, we'll use the overflow rate. And that's the most important parameter for the design of the primary clarifier. Okay, so you will get more practice in the homework examples. All right. Any questions until now? Are we good? Okay. So after the primary clarifier, then we will send the, I would say, the pre-treated water, or let's say somewhat treated water into this aeration tank. So remember, the primary clarifier cannot remove the BOD very effectively. So you still have around 70% of the organics in the water. And sometimes these organic concentration can be really high. So remember, for the industrial wastewater, the BOD can be thousands milligram per liter, right? And our goal at the end is below 30 milligram per liter. So we have to find a very effective reactor to remove these organics. So again, we're going to use this aeration tank as a secondary treatment. So the method we use is to introduce biological components, microorganisms, to eat off these organics or BOD, right? And then we can reduce the BOD concentration in the wastewater. So before that, before introducing the design parameters for the aeration tank, we want to just briefly cover some of the concepts on the biological principles, right? So the overall goal for our aeration tank is to remove the organics and the nutrients using the microorganisms. So we do both of these in the same step, right? Because the microorganisms, in order for them to grow, they also need to rely on nutrients, right? So while they're removing the organics, they're also removing the nutrients during this aeration tank system. So to remove these components by the microorganisms, we have to rely on the microorganisms' metabolism, right? So basically, the metabolism is all the biochemical activities that's performed by the cells. So they can eat off those organics, they can discharge the waste, they can also use the organics or the heat, the energy to propagate themselves, right? So that's why under the metabolism, people further divide the metabolism into two components. One is called the catabolism. So catabolism just means the process where the substrate or the food gets degraded, right? So it's just the oxidation of the food which provides the energy, right? So you can treat that as a chemical process where you convert sugar into carbon dioxide and water. And then at the same time, there can be anabolism. So anabolism is just the cell growth. It's the synthesis process where the cells or these microorganisms utilize the energy that's produced from the catabolism to produce their body mass, right? It's using the energy. So overall, let's say for this entire process here, we call that as the metabolism, right? We call this entire process as the metabolism, but then catabolism is just one part of it. It's just the oxidation of the organics, and then it produces the energy. And then anabolism is to use this energy and then use some of the raw materials to build up new cells, right? So this is very similar, or it is related to um, the the definition of biochemical oxygen demand when we discuss the BOD, right? So we said the BOD is more realistic way to describe the oxygen demand, mainly because the BOD considers the cell growth, right? So not all of these organics are being converted into energy. So some of them are converted to the cells, right? So the BOD is more realistic, while the COD only considers the degradation of the organics. Everything gets produced into carbon dioxide and water, right? So basically there are catabolism and anabolism occurring as a part of the metabolism, right? So then I think when we discuss the different types of respiration and then the different cycles of the elements, we also briefly covered different types of decomposition mechanism or respiration mechanisms. There can be aerobic respiration or aerobic decomposition, which is just to convert the organics into carbon dioxide and water by using oxygen, right? Aerobic means they need to require oxygen. So the end product will be carbon dioxide and water. And then in this process, it actually releases a large amount of energy, right? So this is regarded as a more complete conversion of the organics into inorganics, right? So because of this large amount of energy, they can result in a high growth rate of the microorganisms. And then it also means that we're going to produce more sludge out of this aerobic decomposition. So what that means is that inside this aeration tank, since we bubble a lot of air, right? So the bacteria are going to go through the aerobic decomposition. So they're going to decompose this BOD here. And at the same time, they produce a large amount of energy. And also that will support a faster growth of the microorganisms. So in the end, you are going to have more sludge or more solids getting formed in the secondary clarifier, right? So that's happening. This is what's happening in the aeration tank. So during the aerobic decomposition, there's also, because of this large amount of energy, so the reaction rate is also higher, so you have less odor. So the odor are mainly the volatile organic compounds, those hydrocarbons that's formed from this decomposition. So since aerobic decomposition is a more complete conversion of the hydrocarbon into carbon dioxide and water, so you're going to have less amount of hydrocarbons being formed in this process. And aerobic decomposition is also the natural water's self-purification process. So if you recall, when we talk about the river water quality and then the DO sag curve, right? So you have the sag curve of dissolved oxygen, then the biochemical oxygen demand are actually getting reduced due to the aerobic decomposition. So that's why you have a decrease of the dissolved oxygen in the water, right? So that's the aerobic decomposition. So there's also anoxic decomposition. Anoxic decomposition relies on the nitrogen. So you have this NO here, right? Aerobic, this is related to oxygen. Anoxic is related to nitrogen, right? So for this process, instead of using oxygen as the oxidizer, the bacteria can use the nitrate or nitrite as the oxidizer. So the end goal is the same, that is to convert the organics into carbon dioxide and water, but then you have another byproduct, that's the nitrogen. So you convert these nitrate species into nitrogen. So similar to aerobic decomposition, so the anoxic decomposition also release a large amount of energy, and then which means that it can support a higher biomass production, right? So people use this method to remove the nitrate or nitrite species. So these are the nutrients, right? So we use this process here to get rid of the nitrogen species in the wastewater. So the wastewater contains less amount of them, so it's less likely to have algae blooms coming out of the discharged wastewater. So we use the anoxic decomposition mainly for the denitrification process. Okay. So apart from the aerobic and anoxic decomposition, there is this third type called the anaerobic decomposition. So anaerobic decomposition is a process that cannot or do not require oxygen or nitrate or nitrite species, right? So actually, anaerobic decomposition only happens when you don't have these species, okay? So instead of using these oxidizers, the bacteria will use the sulfate, carbon dioxide, and then organic matter as the oxidizers to produce energy. So it's similar to the process where you have the fermentation or we produce yogurt, right? So when we're trying to convert milk into yogurt, we have to seal the bottle. So there cannot be any oxygen present in the bottle there. If there's oxygen, then the milk will go bad, right? So it's completely into a different process there. So for this anaerobic decomposition process, it has a lower biological energy production, mainly because the conversion of the organics into the waste is not going to carbon dioxide, right? So it's going to different types of hydrocarbons. So it's not a complete conversion of the organics. So that's why you're going to have less amount of energy, slower growth. But at the same time, people produce, I would say, value-added products or more valuable products coming out of decomposition. For example, when we talk about yogurt, we're using fermentation or this anaerobic decomposition to convert milk into yogurt, which is, I would say, more popular, right? It's value-added products. And then we can also convert the organics into methane gas or biogas, or people also call them as syngas, right? So we can use these gas species to produce energy, right? So in a lot of the rural areas, people actually put their waste into somewhat like a sealed tank there, where there's no direct contact with oxygen, and then people can use the biogas coming out of it as an energy source, right? So here I have a short video to show you, let's say this is the syngas, I would say the natural gas, methane gas directly coming out of the marsh area, right? So especially here in the South Florida, we have this Everglades National Park is considered as the marshy area. So you have a lot of plants, right, beneath the water, right? So then when they decompose, they have to go through the anaerobic decomposition. And then from that process, you actually produce methane out of the decomposition. Okay. So I'll first stop the sharing. And this one.
Okay, this is for collecting the methane. It's made out of a Tupperware dish with a brass fitting and a piece of tubing. This piece of tubing is sealed on one end, and for this part of the experiment serves as a plug. Get all the air out.
This is very straightforward. It's just directly capping the gas from the water. Then you can see methane getting formed. During the daytime, it's actually difficult to display because during the daytime you have photosynthesis, right? So you produce oxygen. So it's more of a aerobic decomposition. But at nighttime, when you don't have the photosynthesis, right? So you don't have oxygen there, and then you start to have anaerobic decomposition forming methane. There's a large amount of fuel coming out of the marsh too. If you consider the area for this cap here, it's just a small cap area, right? Okay, just stop over here. Okay, so these are the different types of the decomposition, right? So, okay, so here is another quiz question, right? So aerobic bacteria grow faster than the anaerobic bacteria. Why is it? Let me launch the quiz. Okay, so most of you got it right? So it should be the first one. The aerobic process produce more energy and it can be used to synthesize the body of the bacteria, right? So that's why they grow faster. So because of that, in the aeration tank, right? So you're going to have this accumulation of the bacteria. So you have to add a secondary clarifier to get rid of those newly formed bacteria. Okay. So now let's get back to this aeration tank, right? So we said that overall this process involves, I would say, the cycling of the bacteria, right? So it's not only like a one-way reaction here. So you have influent going inside the aeration tank, but at the same time, you need to produce the bacteria at the beginning so they can eat off those organics. And then the treated water from the aeration tank will go to the secondary clarifier, and then we extract some portion of the collected activated sludge back into the aeration tank, and then while some of them directly go to waste, right? So then here is going to involve some calculations because to design a fully functional aeration tank, we need to basically provide the right amount of bacteria to deal with the organics, right? Deal with the organics in the aeration tank. So before we directly show these equations, let's first design, or define some parameters related to the secondary treatment. So for the secondary treatment or the aeration tank system, people also call it as the activated sludge process right? So they can have different names, but overall, they're just the biological treatment of the BOD in this aeration tank. Okay, so there are several components. This is another, I would say, more conceptual sketch here. So after the primary settling tank or the primary clarifier, we introduce the effluent water into the aeration tank, and then to the secondary clarifier, and then some portion of this activated sludge will go back to the aeration tank. We also call that as the return sludge, right? So return sludge, and then the remaining sludge go to the waste, and then there's also effluent of water coming out, so you can discharge them. So in this process, we have different names, right? So we have the aeration tank. This is basically the reactor where the bacteria and pollutants are going to react, right? So there's mixing and aeration taking place. The reason why we add aeration in this tank here is because the BOD in this tank here is going to be very high, right? It's directly coming out of the primary clarifier. So they can be thousands, right? Thousands milligram per liter. So if we just add bacteria inside, but not providing any oxygen, then those bacteria will die, right? So here we add in this, let's say, air compressor or bubbling mechanism to aerate the water so we can produce sufficient amount of oxygen so the bacteria can still eat off those organics. So after this aeration tank, right, so you have the bacteria, and then those bacteria also populate themselves or propagate themselves, right? So then they become suspended solids. So we have to deal with those suspended solids in the secondary clarifier. And then inside this aeration tank here, we have this definition called mixed liquor. So the mixed liquor is just the solution in the aeration tank. Okay, it's the mixture in the aeration tank. So the mixed liquor is going to contain both the liquid and then the suspended solids, right? So we have this MLSS, stand for mixed liquor suspended solids. So they're the suspended solids in the aeration tank. And further, among these suspended solids, some of them are bacteria, right? I would say a large fraction of them will be bacteria. So that's why people also define this MLVSS. So V stands for volatile. So MLVSS is just the microbial concentration, the microbial suspension. Okay. So in general, for this aeration tank system, the MLSS, right, the suspended solid concentration is going to be 2,000 to 4,000 milligram per liter. You can see this is a very high concentration, right? And then, but among these MLSS here, more than half of the suspended solids are actually microorganisms, right? So if you recall in the beginning when we showed the picture of the aeration tank, right? So they have this brownish color here, right? Actually, half of the suspended solids in the wastewater or in the water here are just the bacteria. So they are bacteria that's helping us dealing with the organics in the water, right? So the MLBSS over MLSS is more than 50%. So that's why there are more than half of them suspended solids are microorganisms. So you could potentially use an even higher MLBSS, more bacteria, right? More bacteria will mean that they're more effective, but their maximum concentration is actually limited by the air requirements because we're bubbling air inside. If you introduce too much of these bacteria, then they're limited by the oxygen, so they will die off, right? And then it also depends on the clarification capacity, so the size of the secondary clarifier. So if you put in too much of the bacteria in the aeration tank, then the clarifier cannot handle them very easily, right? So that's why people still use this fraction here, and then their concentration, actual concentration, are constrained by these requirements. So during the operation of the aeration tank, we also need to pay attention to the amount of dissolved oxygen, right? So because we cannot let the bacteria to go to the anaerobic decomposition, because if you don't have oxygen, then you don't have a large conversion of these organics into carbon dioxide and water. And more importantly, it's going to create, when they get to the anaerobic decomposition, they're going to create different types of VOCs, volatile organic compounds. So you're going to create a lot of odor from that process. right? So we have to ensure that there are sufficient dissolved oxygen. So they must be sufficient for good BOD removal. So normally people set up the dissolved oxygen concentration to be around 2 milligram per liter because we're pumping in an endless amount of oxygen, right? So if you use too high of a dissolved oxygen, then that's a waste of energy, right? You need to use stronger pumps to put in more dissolved oxygen. But at the same time, we don't want the concentration to be too high because the bacteria will live too happy, right? If they become too happy, then they form these filament bacteria. So these filament bacteria, they're like the flocks. Remember when we discussed the coagulation and flocculation. So they behave like flocks, feather-like. So they don't settle down really well in the water. But if the dissolved oxygen concentration is too low, then you don't have sufficient BOD removal, and then you're also going to create this odors associated with the anaerobic decomposition. So that's why we normally set it up at around 2 milligram per liter for the dissolved oxygen. Okay, so then this is, I would say, even more conceptual diagram of the aeration tank process. So now we just treat this part as the aeration tank, right? This part, the circular thing, as the secondary clarifier. So now we're going to build up a mass balance of the suspended solids and also water in this system, okay? Because in order to design this fully functional secondary treatment process, we need to find out what should be the flow rate, let's say to the waste, what should be the flow rate being the return sludge. For the return sludge, what should be the effluent flow rate, what should be the influent flow rate, and so on, right? So first, regarding the mass balance of water, so what we can do is we can just draw this imaginary boundary here, right? So we know that the influent flow rate that's going into this secondary treatment, if we call it as Q, then it's going to be the flow rate going to the effluent, which is the discharged water into the lakes or rivers, and the wastewater, right? So that's the waste coming out of the sludge at the bottom of the secondary clarifier. So because of that, if we write out the equation, so if we still use Q as the influent flow rate, then the effluent flow rate, if we call that as QE, and then the waste flow rate as QW, then we know that QE will equal Q minus QW, right? Because the summation of these two flow rates, should equal to the influent flow rate, right? So this is a mass balance of the water for this entire system. But then further, you can see that, well, for this this sludge here, activated sludge here, a fraction of them go to the waste, but a fraction of them actually was returned, right? Returned to the inlet of the aeration tank. We call that flow rate as QR, right? That's a return sludge. So further, we can build up this flow balance that, well, the flow rate going inside this aeration tank is going to be the influent flow rate plus the return sludge, right? So here you're going to have Q plus QR. This is what's happening over here. So then at the effluent of or at the outlet of the aeration tank, you're going to have the same thing, Q plus QR, right? And then for the effluent, right, for this secondary clarifier here, you also had the mass balance of water, right? So you also have the mass balance of water. So the inlet is going to be Q plus QR, right? This is in for the secondary clarifier. And then if you consider the out for the secondary clarifier, so first you have this QR plus QE, right? Because the activated sludge is being split for the return sludge and the waste sludge. So you have QR plus QE. And then the other out is just it's not QE, it should be QW, right? This is QW. Because they're going to the waste and the return, right? So QR plus QW. And then on the effluent side, that's QE. So we further know that QE equals Q minus QW, right? So if you add these together, right, two outs together, you see the QW got canceled. So we still make the mass balance work, right? In equals out, Q plus QR, right? So you have Q plus QR on both sides of the secondary clarifier, okay? So this is a mass balance of water. So then we could also set up the mass balance of the suspended solids, okay? So here we'll just set up the mass balance surrounding this secondary clarifier, okay? So if you consider the influence of the suspended solids into this secondary clarifier, we know that, well, we have the flow rate, Q plus QR, right? And then the influence of the suspended solids is just this flow rate multiplied by the suspended solid concentration. That's MLSS, right? The total suspended solid in there. And then if you consider the outflow of the suspended solids, so first you have this activated sludge, right? So that's going to be QR plus QW multiplied by SSW, right? So that's the activated sludge. The suspended solid is in the activated sludge. And then at the same time, in the effluent, there's also suspended solids. That's the flow rate, Q minus QW. And then you multiply that by the SSE, right? So then this is outflow of the suspended solid. This is inflow of the suspended solids. Then these two should equal each other. Okay, so we have this mass balance equation built up. So why is that important? And this is mainly because, for example, if the EPA wants to, or let's say the wastewater treatment plant wanted to see if the suspended solids, let's say the configuration of the aeration tank is correct. For example, it's trying to see what should be the return sludge flow rate, right? Because we know that activated sludge can get formed here. You have a pump to pump in the return sludge. So he wants to find out, what if I double the amount of return sludge? How is that going to affect the suspended solid concentration, right? So then, so under that situation, well, the mass balance still works, right? But at the same time, you can measure what is the suspended solid concentration in the effluent, suspended solid concentration in the waste. So you can determine these factors, right? And you can also do the measurement of the suspended solid concentration over here, right? So then you can more easily find out how does the flow rate affects the entire operation of the aeration tank, right? So this is related to the design of the aeration tank system, okay? So I, I would say that we're going to come back to this mass balance equation and then do some calculation in our next class. But here there are a few more definitions, right? So one more definition is the hydraulic retention time. This is just the residence time of the bacteria in the aeration tank, right? So it's just the flow rate, the volume of the tank divided by the flow rate in the tank. So there's also a retention time called the solid retention time. So the solid retention time, people also call that as the cell residence time in the entire system. Okay, so if you consider the cells, the bacteria in the entire system, right? So you need to consider the total amount of cells in the system. So if you want to find out like how long they stay in the system, then we know that the cells are exiting the system through the effluent, right? So they're going out from here. So the mean residence time of the bacteria in the system is just the total amount of bacteria in the system divided by the outgoing rate of the bacteria, right? So you have the reservoir here, and then they're going out at certain speed, right? So the mean residence time of bacteria is just the total amount of bacteria divided by the I would say the outflow rate of the bacteria. So that's why in the mean residence time, or people define that as a theta here, you can see the calculation is just based on the solid, the amount of the solid in the system, the MLSS multiplied by the volume of the aeration tank, and then divide that by the SSE multiplied by QE. So that's the outflow rate of the suspended solids plus the outflow rate of the suspended solids in the waste, right? So one is in the effluent, one is in the waste. And then that's the denominator, and then the numerator is the total amount of suspended solids in the aeration tank. So basically, these are the two different times. So one is the hydraulic retention time. That's the overall residence time of water in the aeration tank. You just use the volume of the tank divided by the flow rate of the water. And then there's also solid retention time. That's in that case, you have to consider how much solid are there and then how fast these solids are exiting from the system. So for this solid retention time, if it's too low, you cannot grow sufficient bacteria. And then if they're too high, then you have a poor settling of the particles, right? Because they stay for too long, and then their mass actually grow too large, and then you have those flocks getting formed. Okay. So there's one more definition. So as you can see, there are probably just too much definitions here. We'll get to these example problems probably in our next class. So one last definition that is called the food to mass ratio. Okay, so the food to mass ratio is the ratio of the influent BOD per day, or people also call that as BOD loading, to the mass of the total organisms in the tank. Okay, so what that means is that basically, if you consider these bacteria, let's say as animals, for example, as I would say as a rat, right? So the food to mass ratio is just the amount of food you provide to the mat divided by the mass of the rat, right? So basically, it's considering how much food this rat can eat per day. Okay, so in general, for the wastewater treatment plant, the food to mass ratio is 0.2 to 0.5 per day. So basically, these bacteria are really good eaters, right? So they eat around 20% to 50% of their body mass per day. If you consider a human, right? So we probably eat 1 or 2 kilograms of food per day. But these bacteria, I mean, that's probably 1% or 2% of our body mass, right? But these bacteria eat a huge amount of organics. So that's why they're being selected in the aeration tank, in the treatment of the BOD. So this food to mass ratio is calculated by the BOD loading divided by the total mass of the organics, right? The BOD loading is just the BOD multiplied by the influent flow rate, right? So if you recall the schematic diagram, that's the flow rate over here. So you use BOD to multiply that, that's the BOD loading. And then the food to mass ratio is just the BOD loading divided by the total mass of the microorganisms. And the total mass of the microorganisms is just the MLVSS multiplied by the volume of the aeration tank, right? So if you consider the unit for these two terms, the BOD loading, so the BOD concentration is milligram per liter, and the flow rate is, let's say, a liter per second, right? So you have the BOD loading being milligram per second, right? You have a unit for the BOD loading. And then regarding the total mass of the microorganisms, so MLVSS, you have the unit of milligram per liter. And then this volume here is just a liter, right? So then if you cancel these out, you can see that the food to mass ratio is just has a unit of inverse second or inverse time, right? So it represents how much food, what is the percentage of the body mass is being consumed by the microorganisms per second or per day. So if you give it too high of a food to mass ratio, then these microorganisms cannot handle these amount of food, right? So they're going to, so you have an inefficient processing of these organics. And then there's also a process called the viscous bulking. right? It's because you have too much organics inside and it gets too viscous or too sticky for the wastewater. So then in the secondary clarifier, you're going to have a poor settling. But if the food to mass ratio is too low, again, these bacteria becomes too healthy, right? So they become too happy, and then you form this filament again. So filament bacteria again. So then they have this poor settling phenomena. Okay. So let's just stop at here. So I would say today we covered probably too many concepts about the secondary treatment. And then in our next class, we're going to go through these example problems and eventually a design problem, like a complete design problem for the aeration tank or the secondary treatment process. Okay, so that's it for this class. Any questions until now? Okay,
No.
yeah, thank you. And
Bye.
I will also post the homework problems on the Blackboard. All right, see you guys. Have a nice weekend.
Bye.
Thank you.
Bye.
Goodbye.
Bye.